the title of her talk is Beyond MHD Simulations of Atmospheric Dynamics. Elena. I mean, we can wait 2 minutes.
Yeah, I can do it. Hi.
Just wait for 2 minutes. People are joining in. I think we are not yet 2 o'clock here.
Yeah, I see the auditorium is empty.
So we are not getting so many people in the auditorium. Everybody prefers.
Yeah, we can wait a bit.
Yeah. You won't see many people in the auditorium, but most of them are joining from their offices. But still, we can wait for 1 more minute. Maybe Anusha, you can start. You can introduce the speaker again. Start it.
Yeah. The first talk is by Elena Komeko. She will speak about Beyond MHD Simulations of Atmospheric Dynamics. Elena, over to you. I will signal at 3 minutes before 30 minutes.
So shall I start?
Yeah.
I can start. Okay, so shall I do full screen? It's really nice to be talking on this conference virtually. I would prefer much to be there in person, but the circumstances are like they are. So there is not much we can do. So I've got to talk today about the modeling, and I will be biased by my personal preferences, which goes beyond MHD modeling of solar atmosphere. And when I say beyond, what I mean here is essentially introduction of neutrals in MHD simulations. So as a matter of introduction, all of us, we know that solar atmosphere is a strongly stratified medium because we have gravity and because we have stratification in horizontal and vertical directions. And also, we know that the photosphere, that the region that we see with the naked eye, is a strongly collisionally coupled medium. But we also know that this medium is only weakly ionized gas. So essentially, we have very, very few ions there, and mostly it is dominated by the gas pressure forces. When it comes higher up to the chromosphere, we know that the chromosphere is much less collision coupled because the density drops, and the chromosphere also has a significant neutral fraction. And the chromosphere is a transition layer between the corona and the photosphere, and there we can have situations where the plasma is either gas dominated or magnetic dominated. That would depend on the magnetization of a given region. And then on the top, we also have corona, which is fully ionized and that is magnetically dominated and almost collisionless. So globally, we can ask ourselves several questions, like, for example, this one. If we have all this magnetic energy in the interior and it needs to propagate in the corona, and we see all these manifestations in the corona of this magnetic energy, how does it come to propagate through the layer of the photosphere and chromosphere where we have that many neutrals, and how is this interaction with neutrals happen, and what are the consequences for this magnetic energy that needs to reach the corona? And in this regard, are we in the position, is it even possible to model these ion-neutral interactions, and especially in realistic solar situations? And this is so because interaction with neutrals, of course, they happen at very small spatial and temporal time scales and spatial scales related to these ion-neutral collisional distances in time and in space. And if you want to resolve these scales correctly in, say, realistic simulations, it becomes really progressively more computationally costly. So is it even possible to model this correctly and at the same time having realistic simulations, like those that we need to compare with observations? And the last question is that, what is the minimum amount of physics that we need to include in our MHD modeling to improve it and to correctly describe ion-neutral interactions? And do we need to worry about this at all? Maybe we can still go with MHD and we don't need to worry about life beyond MHD. So this is what my talk will be about. The field of modeling beyond MHD, and in the case I'm speaking about is due to neutrals, it has been a popular field recently, and it has been recently growing. So there have been many groups joining into this effort to model solar plasma beyond MHD. And there essentially have been like two strategies. One of them is a strategy where we produce large-scale realistic modeling. And in this case, this is essentially what we call single fluid approximation, because this approximation allows you to still use your MHD codes with very little effort. And what we want to do is to go from this situation, which we have observations in the chromosphere, and we want to model them and obtain them in the simulation box. And you might see that in this case, this is a Bifrost simulation that many of you have been using, and that does not look quite like the chromosphere because there are still some differences in there. So we are trying to improve in this like a community, and ideally we want to have the same, right, from one to another. So we are trying to see if by including this new physics, we can get from this situation to the modeling situation and improve it. When we talk about single fluid effects, those are essentially these three effects that we are talking about. And the most important of it is what we call ambipolar diffusion, because these mechanisms, due to collisions between ions and neutrals, it dissipates currents perpendicular to the magnetic field. And this is very effective in producing additional heating because of this friction between the components. And of course, this additional friction is welcome when we want to heat the chromosphere and corona. And as a bonus, this ambipolar diffusion relaxes your magnetic structures to force-free situation because it dissipates perpendicular currents. And on the top of that, then there is also a modified Hall effect. And when I say modified, is because it's the same Hall effect, but now it acts on lower frequencies because it is modulated by the ion fraction. So the frequencies becomes as lower as the ion fraction is. In the photosphere, it can be 4 orders of magnitude. And theoretical investigation shows that it helps Alvan wave production, which is good because Alvan waves can bring energy to the corona, and this is welcome as well. And there is a very tiny Biermann battery effect that you can easily neglect. And the only thing it does is it helps seeding magnetic field for the local solar dynamo. So it always helps in repopulating the quiet solar areas with magnetic field. And then there is a different group of modeling where people have been dedicating their effort on modeling a particular phenomena at smaller scales. And this mostly was done in two-fluid or multi-fluid treatment. So when you do a particular idealized modeling, then you have a luxury that you can go to very small details, and then you can have boxes with very high resolution, especially if you don't do 3D. You can do in 1D or in 2D. And this idealized modeling mostly was done in application of several particular phenomena, like, for example, structure of rocks, reconnection, and different kind of instabilities. So when we talk about multi-fluid, the most important effects are like those. For example, one of them is dynamical decoupling of species because they are under action of different forces and they're not colliding sufficiently to become a single fluid. It means that if ions feel the influence of the Lorentz force and neutrons, for example, they feel the influence of the friction force or of the viscosity, then they will behave differently and that will produce different in velocities. These velocities of different fluids, the particles will collide and they produce a frictional dissipation. And frictional dissipation is something that is analogous to ambipolar diffusion in single fluid. And what it does, it dissipates the kinetic energy of those motions. And of course, it produces heating. And again, heating is welcome because we want to heat chromosphere at the last instance. And also we have to worry about the ionization and recombination balance because in multifluid and proper multifluid, particles can collide and they can ionize or recombine. And the timescales of ionization and recombination are quite different. And there have been many studies about that. And that what produces is regions where the temperature is far from the one corresponding to thermodynamic equilibrium. And the ionization fraction, of course, is different. And all these fun effects are being studied right now. So in the rest of my talk, I will stop as much as I can on what different groups are doing regarding this multi-fluid or single fluid modeling. And I will start with the multi-fluid effects because I think this is much more fun because it's something new, really new that we are doing now. So where do we stand with the multi-fluid effects? When we talk about multi-fluid effects, so what we have to do, we instead of solving a set of equations that all of us are used to solve, that's one shown on the left, where we have evolution of mass, momentum, and energy of our plasma, we have to add a second set of equations where we have evolution of a neutral component. And these sets of equations, they are coupled through the interaction terms that are highlighted in blue here in this transparency. And you don't need to understand these equations, just need to see the structure of those equations. So these interaction terms are due to ionization and recombination in the mass conservation equation, which have the counterparts also in the momentum and mass and energy conservation. And we have also elastic collisions that produce you this collisional friction and heating in the energy equation. And we have thermal exchange. And on the top of that, we also have pressure tensor that can be anisotropic. And we can have conductivity. Well, then there have been a lot of effort in this direction. And for example, one of the natural situations where you can have this multi-fluid physics are all kind of transitions. For example, this can be a transition between prominence and corona. So this is important for instabilities and prominences. Those can be transitions that we have, for example, in jets and spicules, when we have a fast-moving material from the chromosphere to the higher layers, and then we have Kelvin-Helmholtz instabilities. And all kind of, each time we have a transition, you have to be sure that multi-fluid effect will be acting there. So there have been simulations of Rayleigh Taylor instability in solar prominences in MSD, but now we are moving to really fully multi-fluid description. And for example, the simulation is shown on the right. This is a very beautiful, amazing simulation done by the group of Andre Hillier, where they model Kelvin-Helmholtz instability. And this is just a theoretical modeling. I mean, you cannot apply probably to a particular chromospheric region, but still it's very nice because what they discover is a number of effects that are just simply not present in multi-fluid. For example, they discover that these vortices that develop in these fluids, they are quite different in neutral and in densities. For example, if you just look at the density images, so the structures that you form in neutrals and in charges will be different, and they're also different from the structures formed in the magnetic field. And this decoupling is especially important on smaller scales, so for smaller vortices. And there are different heating regimes. So for regimes where the fluids are decoupled for small scales, there is a constant heating rate. And there is a constant heating rate, so the constant energy input from the fluid, from these motions into the plasma. But when we go to the larger scales, those above the scale of ion neutral coupling, the heating decreases with a power of -2. And it means that we really need to resolve correctly these small scales, because it's where the heating and all these plasma processes are going to happen. There is also an effort to model relative instability at the border of solar prominences. There has been models by the group of James Leake et al. Reported in 2014, where they start initially a modeling where they had a prominence thread, and they had a two-fluid model, and there was a continuous transition between the thread and the corona. And this transition is crucial because it's right in the transition where we can smoothly go from the situation where we have mostly neutral plasma to mostly ionized plasma, and we have the transition from all the different scales. So we can really resolve scales of ion-neutral interaction in this transition. And this work was continued later by my group, by my student Beatrice Popescu, who is now in Belgium. And on the contrary, on the different side of it, you can contrast it, for example, to the single fluid modeling that was done also back in the past, that includes ambiguous diffusion. And in that case, there was a discontinuous interface. And what was concluded in this modeling, for example, that even so in this simple situation and single fluid modeling, neutrals do act. And what they produce is they make that instability, lateral instability happening at all scales, even despite the in-plane magnetic field component. So that becomes unstable always. As I said, the continuation of work by Leake et al. Was done by Beatrice later on, and that was reported. So there are a couple of papers and ideas that you may check if you're interested. And here's a movie from this simulation where we can see how the instability on this prominence thread is being developed. On the left, we see neutral density, and on the right, we see ion density. So if I stop this movie, we may see that the structures that form in different fluids are quite different, because especially at the border, they do decouple. We see that upflowing bubbles are more ionized and downflowing spikes are more neutral. We see the layer of high contrast plasma because of the ionization imbalance surrounding these downflowing bubbles, and that might be having its counterpart also in observations. And we also see different phenomena like reconnection and formation of magnetic islands filled with coronal material. So this is a lot to study here. Another manifestation of this ion neutral effect, as I say, is a decoupling in velocities, because the velocities are of neutrals and ions because they are under action of different forces. And this is what is shown here. So again, what I show is a snapshot of the horizontal and vertical decoupling in velocity from the set of simulations that I have seen before. And we see that the decoupling velocities are not centimeters, but they are a few hundred of meters per second. So this is something that we can really go and measure on a telescope, especially on the high resolution data. And also there are some indications that this decoupling is asymmetric. So if we take all the points in our simulation domain and plot the decoupling velocity in the form of a histogram, we obtain that there are more negative decoupling in a way that this is produced by faster downflows in neutrons because they are not filling the magnetic field, of course, and there are also faster upflows in charges. And so this is an imbalance, and that produces some indications for negative asymmetry in these histograms. And this is again something we can probably check in observations in the future data. Okay, then another field which is also being developed is the development of shocks. And shocks are the discontinuities, and we know that in the discontinuities, the parameters of the plasma change abruptly, and because of that, again, there is a continuous changes of the scales, and that has been known since the 90s in the interstellar medium. So in weakly ionized plasma, there is a complicated substructure of different types of shocks. So there has been a classification, for example, by Drain and McKee, done back in the 90s. And this kind of phenomena are being now found also for the sun. For example, again, the Bockros group of Hillier and Bensnow, they have been modeling, again, very idealized, but still it's very valuable modeling of a propagation, for example, in this kind of, that was just a simple Riemann problem, where the instability, the shock was created by the discontinuity in the magnetic field. And you may check that the velocity in an MHD situation that is shown here by dashed line are like this, But if we take into account a different behavior of ions and neutrals, the distribution of the velocities is by blue and red line, and the difference between them is shown as a green line here. And you see that especially at the discontinuity, these guys, they decouple very well, and then there are a lot of difference in these velocities, and that will produce heating and shocks, and that will produce a shock structure, smoothing of these shocks, etc. These works have been continued as well. So later there are a lot of papers published on this subject. So I welcome you to check them. They're very, very interesting. Here it was the same work of the same group of authors, where they also study the propagation of shocks in the stratified atmosphere, because this is what we need to worry about in the chromosphere. It is stratified. And then they check, of course, they found that even for the longitudinal velocities of this, well, in this situation, there was an inclined magnetic field. So even there, even for longitudinal velocities, there is a decoupling in the shock. And for fast waves, there is a very strong decoupling between ions and neutrals. And this effect depends on the collisional frequency a lot. There has been works also in my group. We have been studying this problem slightly differently. So what we study is the propagation of a wave of a given period of frequency from the photosphere to the chromosphere. And you see here a snapshot of these one-dimensional simulations for the waves of 4 different periods, 1, 5, 7, and 20 seconds. And we see two effects here. So there is a linear situation where we have a linear damping of these waves, and this happens because of ion-neutral collisions. But if we include nonlinear terms, we see that this damping becomes much stronger, and this is because we include nonlinear interactions, which are faster and stronger when we have development of nonlinearities. So if we even include the amplitudes of these waves at the base to reasonable numbers, we see that these shocks, they can completely disappear after some level in the chromosphere. And all this energy of all these shocks, it went into heating of the plasma. So this mechanism is being very, very efficient. There is also works on reconnection. And in reconnection, these multifluid effects, they play also an important role because they allow to decouple inflow and outflow velocities in the reconnection site. So for example, in a simple Harris sheet reconnection modeling done by the group of James Leake and Slava Lukin, they have been looking at how these inflows and outflows change the reconnection rates. And they found two effects. So first, then there is a larger population of ions because of the ionization recombination imbalance in the reconnection site. And these ions, they recombine and they're quickly moved by the Alvan outflow of this region. And these ions to neutral flows are coupled in the outflow, that you can check on the snapshot. And then there is a secondary serine instability that is more propitious to develop here, and that produces altogether an increase of the reconnection rates. So similar things were found also in recent papers by Alvarez Laguna et al., where they also found the formation of these plasmoids to be very important when we include partial ionization into account. And they also found that there is a thinning of the current sheet, same as in previous works. And additionally, the radiation also plays a role because it cools the plasma, and which results in thinner current sheets and faster reconnection. Well, I will not stop here. So I don't think I have much time left, but there has been also a progress in this realistic simulations, including generalized Ohm's law, which is a single fluid. And this is a completely different direction because instead of modeling particular phenomena, like was done before, what people try to model is just to take the whole bunch of the solar atmosphere from the photosphere to corona, as is shown here in this modeling by the group of Juan Martinez Sicora, and in Bifrost simulations, and they include generalized Ohm's law, what they call GOAL here, which is ambipolar diffusion, Hall battery effects. Well, essentially, this was ambipolar diffusion here. And in their initial simulations, they found that if you compare two snapshots with no ambipolar diffusion and with ambipolar diffusion on the bottom, you see that when you have these rising bubbles of the chromospheric material to the corona, they cool because of adiabatic expansion, and there are regions of very cold temperature here. That was always a problem in these simulations, and especially because we don't know if there are counterparts and observations of these cooling bubbles. However, when the ambipolar diffusion is there apparently these bubbles are not present anymore because there is additional heating because of these neutral effects, and they're apparently allowed to remove those bubbles. But the situation is not so simple, as we will see by the end. So bipolar diffusion apparently also allowed them to form longer and faster specules in those simulations. And they have been seen also indications of the decoupling of the plasma motion and magnetic field and specules because, okay, yeah, they are not aligned. Nice. So we have been doing also simulations of those in 3D. And in this case, it's really a situation where we have, unlike the previous one I showed, so where we have a very, very quiet solar region where we have dynamo magnetic fields. So they are really mixed polarity magnetic fields with a lot of structuring, as you may see here. So some magnetic field lines. And the gray areas are the heating places due to ambipolar effect in these three-dimensional simulations. So we've been playing here by having only simulations with ideal MHD, with only battery effect and dynamo acting. Then we have been adding ambipolar diffusion on the top of that and letting it for a couple of hours. And also ambipolar diffusion and the Hall effect. And again, letting it for a couple of hours. And we have been comparing those simulations. And what we see here is that there are many results, of course, but if you just check the distribution of the magnetic Pontic flux and how it reaches the upper layers of our simulation domain, we see two effects. So here on this graph, I show the average Pontic flux as a function of height. And you have to pay attention on the dashed lines because dashed lines is a shear component of this flux, which gives you motions transverse to the vertical magnetic field. Okay. And we see that these three lines, they separate, meaning that the red line is in our MHD battery, say. When we include bipolar diffusion, there is less flux because this flux is being absorbed and it has been converted into heat. So it doesn't reach the upper layers. But when we include the Hall effect, we see that there is an increase of this flux. And we concluded that this happens because when you include the Hall effect, it helps you production of Pontic flux in the form of Alban waves. And you see it very clearly when you start studying vorticity and all the associated motions, because on this snapshot, for example, you see the situation with the Hall effect acting on the left and no Hall effect on the right. And you see that there are these kind of vortex channels that are associated with these vertical magnetic field concentrations that are much more effectively formed in the simulation where the Hall effect is on. And we are still studying why is it so. Okay. And as I said, the situation is not so simple because there are many effects you have to worry about. And one of them is ionization recombination imbalance that needs to be treated really carefully. And there has been a very nice paper of Daniele Nobrega-Siverio last year, where they did simulations of the ambipolar heating of the same kind of situation as I told before, but now including non-equilibrium ionization. And you may check here on the right how the temperature looks like in this case. And we see that, again, when there is no ambipolar diffusion, we have a cold bubble. When there is ambipolar diffusion, this cold bubble is removed. But when we have both non-equilibrium ionization and ambipolar diffusion, there is no such nice removal of the cold bubble. So there is still some heating, but it cannot be as effective as with equilibrium ionization. And this is because of ionization recombination scales imbalance. So we have much more ionization fraction, much larger ionization fraction when we take into account this imbalance as we have in LTE. And this is something that we still need to understand. And I think the way to go is probably multi-fluid modeling here. So we need to combine both fields of this idealized modeling and realistic modeling and to see how we can understand all this together. So this brings me to conclusions. So my conclusions are essentially that, yes, we need to worry about ion neutral effects because they definitely play a major role in the chromosphere. They do so at the contact layers that can be prominence-corona interface, specules, and jets by influencing the stability, by producing additional frictional heating, cross-fuse motions of neutrals. They are definitely very important in shocks because it produces multi-fluid structures or shock fronts and also again frictional heating. It is very important in reconnection because it facilitates plasmoid formation and increases reconnection rates that we need to facilitate the liberation of the magnetic energy. It is important in the current layers because it helps efficient dissipation of the perpendicular currents. And again, it contributed to the chromospheric energy balance in single fluid models. It also may favor production of Alban waves through the modified Hall effect and increase the Pontic flux to the chromosphere. And there are a lot of more going on that I just didn't have time to cover. So if you have questions, please ask me. Okay, I'm done.
Okay, so there is one question given in the chat from Tushar Bhat. Can you please say your question, Tushar?
Yes, actually, I was wondering about what's the main. In one slide, I see that horizontal and vertical view, but I cannot address on which slide. So, please, if you can, Helena.
Yes, and horizontal and vertical views. Let me see if I.
Somewhere in between 5th to 7th slide. Oh, Elena, you are mute. Please unmute.
Is it can be this one?
Yes, yes.
Yeah. So what's the question?
I cannot see your slide.
Oh, sorry. I'm trying to so just let me do it again. I don't know why I stopped sharing like this. Can you see it now?
Yes.
Yes, this one.
Okay, so what's the question?
Yeah, so actually, this decoupling in horizontal velocity and decoupling in vertical velocity. So I'm not actually getting this.
So this is when we have separate evolution of neutrals and ions, right? And you have a discontinuity. So this is relative instability. So you have these drops falling from the discontinuity, right? So neutrals, and there is a magnetic field that stops ions from falling. But neutrals, they are not stopped in principle because they can slip through the magnetic field, right? If there would be no collisions. So that means that if we have very weak collisions, that neutrals, they will continue slipping down through the discontinuity. And the ions, they will be, to some extent, they will be stopped by the magnetic field because this is relative instability. And this is mostly this, and also the action of viscosity on neutrals, which produces this decoupling. So that means that velocities of neutrals on ions on the discontinuity, they will not be the same because they are the action of different forces. And that's why we see, for example, in the snapshot of the vertical decoupling, we see the difference between vertical component of neutral and ion velocity. Okay. And this is the difference. So the lines here is the magnetic structure. So this is the magnetic field potential lines, constant magnetic field potential lines. So you see that there is a magnetic structure, and see that there was a bubble, a flowing and downflowing bubble in this domain. And you see that essentially these are blue regions is where we have more velocity in the negative directions by neutrals than in the ions. Okay. So because they go faster.
Yeah, we have to make our answer short. So I see a question from I Auditorium. Please unmute and ask the question.
Hi, Elena. This is Rajaguru here. I was wondering about your 2D plot of Poynting flux, the height versus frequency. I see a bump around 5 to 10 millihertz there. Is that, yeah, so that one, is that, what is the source of those Poynting flux at that frequency?
Yeah, this is height here, right? So you see that this peak, this representation, this height is essentially in the chromosphere. So these are 3-minute shocks in the chromosphere.
Okay, 3-minute shocks, okay.
3-minute oscillations, essentially, well, shocks as well, yeah.
All right, can I have one more question, Vidya? Yeah. So in your dynamo simulation with the battery effect, you said that it is saturating at 100 Gauss?
Yeah.
What height is this 100 Gauss?
It is in the photosphere at 0 kilometers.
So you don't get kilogauss fields from the...
No, you get kilogauss field concentrations. When I say 100 Gauss, it's an average magnetic field strength. So okay. You have a distribution, so you have kilogauss concentrations here and there in the granular lanes as well. Yeah.
Okay. Thank you.
Yeah, next, Ronnie Kippens. Please ask.
Hello. Hello, Elena. Can you hear me?
Hi, Ronnie.
Yeah, very, very nice overview. Thanks very much. I guess I had a question more related to the local simulations, like these Rayleigh-Taylor simulations that you were showing. Can you comment a little bit more about the scales where the decoupling really happens? I mean, if I infer from this picture, you have here 1 megameter, but that's the whole box, I assume. So what kind of scales do we really see? I mean, is there any hope that we can actually see that directly, or will we have to infer it from these kind of asymmetries?
No, there is no hope. you can measure this directly. I mean, the whole box here is 2 megameters wide and 8 megameters long. So in principle, this is something that you can get. But of course, when you talk about this snapshot of decoupling, right, you see that the regions where we have strongest velocities, they are very tiny. So in the paper by Beatrice, you may check and there is a figure with the scales. So you can see at which scales there is the decoupling is happening.
Maybe what about laboratory experiments? Because these things can be
laboratory experiments, yes, you do, because in tokamak devices, they really worry about neutrals because by the edges of the device, they have a formation of neutrals and then they have a lot of decoupling. So there you can measure this. Yeah, in fact, yes. But what I want to stress, because I mean, you cannot go point to point, like do this snapshot and observations, but maybe the average effect is still there because you have this imbalance between what goes up and what goes down. And maybe this can be a kind of indirect indication of those effects and observations, if you want to check that.
Thank you. Thank you.
We can request Arnabda, please ask your question. And by that time, the next speaker can start sharing your screen.
Okay, so you have stressed the importance of going beyond MHD at the chromospheric level, but as we know, as we go up further, the temperature increases and presumably the corona is fully ionized. So now we know that many years ago, for example, Hartle and Sturrock considered a two-fluid model of the solar wind. Of course, they considered ion fluid and electron fluid, not the neutral. So my question is that the neutrals play important role up to what height? And is it good enough to apply MHD to corona, or for corona or solar wind also it's necessary to go to multi-fluid models beyond MHD?
Well, neutrals are definitely important at the base of the corona because when we have this material rising from the transition regions, this is a corrugated region. So there are neutral material reaching the corona at the base. So there are up to lower corona, I think we have to worry about neutrals. But then maybe higher up, you can go well with ions and electrons. But I don't want to enter the corona because I mean, there you can enter the field of kinetic modeling and whatever. So it can be really up to choice of someone how to model corona best. But the neutrals, they can be maybe up to few tens of megameters from the base of the photosphere. They can still be important, I think.
Okay, I think we have to now next move to the next speaker.
Thank you, Elena, for your nice review. The next speaker is Piyali Chatterjee. Her title is MHD Simulations of a Repeatedly Flaring Delta Sunspot. Piyali, over to you. I will signal before 3 minutes.
You are on mute.
We cannot hear you.
No, yeah, Piyali, you are mute. Okay, I have to unmute. You have to unmute. You are still mute.
Yeah. Now is it okay?
Yeah.
Yes.
Okay, now we do not see your video.
Now can you? You don't see anything now. Okay. Yeah, just a minute. Now do you see?
Yes, you need to make full screen.
Okay. Yeah, sorry about that. Okay. Let me just go to the full screen.
Perfect.
Yeah. So yeah, thanks. Sorry about that. Okay, so thanks to the SOC for giving me this opportunity to present my research on repeatedly flaring delta sunspots from the point of view of MHD simulations. So, of course, it is, everybody here knows that the delta sunspots are formed when there are two or more umbras inside a single penumbra. And studying these delta sunspots are very useful because the 95% of X-ray producing X-class flares actually originate in these delta sunspots. And they are known to flare repeatedly, which means that they're likely to be geoeffective. And another observation is that there exists some amount of flux imbalance, magnetic flux imbalance between the components of these umbras inside this penumbra. So that is also an observational fact. Now, delta sunspots have been traditionally classified by this old paper by Zirin and Liggett into 3 types. So the first type, type 1, corresponds to the spots, delta sunspots, where all the spots emerge together at the same time, almost at the same time. And there are type 2s where there is an old, well-established sunspot, and satellite sunspots emerge near it and often show very large rotation. So these are type 2 sunspots. The third kind of delta sunspots are those which are formed due to collision and merging of 2 different flux systems and often belonging to different bipoles. A classic example of that is the AR11158 sunspot. So basically, I would present a proof of concept simulation to understand why that is the case, focusing on the type 3 delta sunspot. So why is it that the collision merging of such bipoles lead to repeated flaring? So our tool would be the pencil code, which is a multi-user open source code and maintained as a live repository on GitHub. So this code is actually equally efficient for the quiet sun as well as for eruptive phenomena. So to test our assertion about this collision merging of delta sunspot and repeated flaring, we set up a convection in a box where we place the box at a co-latitude theta. For this case, we have placed it in the northern hemisphere. So the omega is, so the rotation axis is in omega direction, whereas the vertical is the z direction. So for reference, the dimension of the box is 36 by 36 megameter horizontally and 25 megameter in the vertical, out of which the lower 10 megameter is convection. So once the convection has been set up, we introduce a neutrally buoyant magnetic flux sheet inside the domain near the lower boundary. And in this flux sheet, the magnetic field is horizontal and is constant. And initially it is neutrally buoyant, which basically means it has the same density as the surrounding. So it doesn't start to rise immediately as we put the flux sheet in. And this flux sheet has a very small aspect ratio, about 0.1. So why should such a flux sheet be considered in such a simulation? So one thing is we can consider it as a new technique to generate complexity in flux emergence compared to the normal flux tube emergence, flux rope emergence models. And also such a layer might be generated due to the action of near surface shear layer. Or if you like in case of omega loops, these thin layers can form when rising flux tubes have been squashed because of this rising process. As you see in this simulation by Nelson et al., you see the tops are very squashed. So such a layer, we cannot rule out the presence of such a layer in the subsurface. So now what happens when we introduce this layer is that it breaks up into tubes because of what is known as magnetic buoyancy instability, which is actually a very well-studied instability. And once it breaks up into tubes, they become buoyant and they emerge out of the photosphere. So the regions where these flux tubes are intersecting the photosphere, we can call them as synthetic sunspots. So now in an earlier work, we had tried to measure the alpha effect that comes about because of such a magnetic buoyancy instability. So we calculated what is known as the alpha tensor inside this magnetic layer by placing it at different latitudes given by lambda. And we found, like the traditional turbulent alpha effect, this alpha effect also goes to maximum near poles and changes sign at the equator. So the diagonal components are the pseudoscalars, as the off-diagonal components are not. Now, such a self-consistent generation of twist because of an alpha effect can lead to what are known as bihelical fields, because of course the helicity has to be conserved. Now, these bihelical fields means that you have a field of a certain twist, and just next to it there's a field line of an opposite twist, and that can have strong implications for magnetic reconnection, and it might make it easier for reconnection to happen in case of flares, for example. So one of the important novel aspects of this kind of flux tube, multiple flux tubes generated through this magnetic buoyancy instability, is that these tubes have non-uniform twist. So as you can see in this picture, so there's a region of large twist and there's a region of small twist. So it's only this region of large twist that can overcome the subadiabatic gradient of the photosphere and emerge out to form sunspots. So this gives rise to some amount of natural selection in what part of the flux tube will emerge and what part is not going to emerge. So going ahead, when these multiple flux tubes emerge, they actually coalesce and they give rise to two very dominant spots, which actually collide and merge together to form a delta sunspot-like structure. So here you can see about 4 hours of solar time in this movie here. So you can see the magnetogram, and overplotted is these contours of temperature, which appear like lightning strikes, and they correspond to multiply flaring delta sunspots. Multiple flaring delta sunspot. So this delta sunspot actually gave rise to 4 different flares. So we analyzed 3 different flares here. So these arrows indicate the epoch where the flare events occurred. And by the analysis of this energy release process, we can approximately say that these flares were of B and C class, corresponding to that in the sun. Additionally, in the region where the flare actually occurred, we see occurrence of bidirectional reconnection jets. So as you can see here in this picture as well. So they can be, the velocity of these jets can be as high as 200 kilometers per second. Apart from that, if you look at how the foot points of the magnetic photospheric foot points of the magnetic field lines in the atmosphere are behaving, so we see a lot of shearing and convergence. And as we heard from Alphonse Sterling in the first talk of this meeting, that these moving magnetic fields show a lot of cancellation before a repeated eruption. So we see this repeated coronal flux rope formation and sigmoid to cusp to sigmoid morphology, which is a very strong signature of homologous flaring active regions. And this is also seen in observations of soft X-ray sigmoids. So you have a sigmoid to cusp to sigmoid and so forth in the H-alpha filament case for an observed active region. So in our simulation, we also see formation of a filament or a prominence by thermal condensation and supported by the magnetic tension of the magnetic field lines. So in summary, with a very simple and primitive initial condition and making no assumption about the properties of the subsurface flux tubes, like how big, what is the radius, what is the twist, even without making any assumption, we have managed to produce a delta sunspot-like feature, which shows non-uniform twist, and it's formed due to collision merging, so it's kind of type 3, and it flares repeatedly, and energies correspond to typical C-class flares on the sun. And we also observe exotic phenomena like in situ flux rope formation and filament formation. So to end, this flare simulation dataset is available freely as 3D snapshots of temperature, density, and magnetic field and velocity. So if anyone is interested in analyzing it further to understand how the magnetic field, for example, is behaving before and after a flare, or do some forward modeling, you are invited to write to me, and I'll be happy to share data set. Thank you.
Okay, thank you, Piali, for giving nice talk. Okay, now I will take the question. So, Ronnie Kippens, please unmute and ask your question. Yeah.
Okay, thanks, Piali. I had a question about the actual equations that you're solving, and especially what kind of physical terms do you account for in your energy equation? I asked that because you hint at the end of filament formation, but I'm wondering what kind of ingredients do you have to drive filaments here?
So we have this thermal conduction, and then we have this optically thin radiative cooling. So I think it is because of that. It doesn't have radiation. It doesn't solve detailed radiative transfer, but there is this optically thin radiative cooling.
And so did you make direct contact with linear stability criteria from thermal instability?
No, I did not analyze it further. So I only checked that there is a filament. I mean, there is a dense region which is being supported by this magnetic field. But if you ask me what was the growth rate of that, and was there any, basically a growth rate or the linear regime of this instability, no, I have not yet looked at that.
Okay, thanks.
Okay.
Okay, next we'll take a question from Venkat. Your name appears as Galaxy 7. Please unmute.
Hello. Yeah. Yeah. You were. I was curious to see. You were telling all the time C-type flares were produced. Okay. So, can you hear me?
Yes, I can hear you.
Yeah. So I was wondering why was it limited to C-type? Because usually this X-ray classification depends only on the electron density in the flaring plasma. So, have you any control over the electron density? And if you can, so you get X-ray flares.
So the way we estimated that this is B and C class is from these energy estimates that you can see on this slide. If you can see the slide that I have projected right now. So the energy was between 10 raised to 29 to 2 into like 3 into 10 raised to 30 ergs. So there are these estimations from thermal energy, kinetic energy, X-ray, and everything. By Isobe et al. I think I have not put up that reference here on this slide, but they said that if you have this much of energy release, it basically means that the flare class is P or C or X or M or whatever. So in that way, so I have only analyzed the energy release in the model and then just equated it to that range given in this. So I have not calculated the X-ray flux directly. To your question that why is there no X-class flare? Yeah, that may be because these regions, the magnetic flux that we emerged was of the order of 10 raised to 20 to 21 Maxwells. So that is, it is a small region. I have computational limitations, so it's a small region. So if I was able to take a bigger region with a larger magnetic flux, I'm sure I would have had M and X class.
Okay, thank you.
Okay, so if you do not have any more questions, then I will thank the speaker once again, and we'll move to the next speaker.
I'll just stop sharing.
Thank you, Piali. The next speaker is Manuel Luna. Title is Large Amplitude Prominence Oscillations Following the Impact by a Coronal Jet. Manuel, over to you. We can't hear you. Manuel, we cannot hear you.
I know. Now?
Oh, yeah, we can.
Okay. Good morning. I'm Manuel Luna from the Balearic Island University in Spain. And this work has been done in collaboration with Professor Fernando Moreno Inserti from the IAC in Canary Islands. And in this work, we try to understand the possible interaction between a coronal jet and a prominence. And let me introduce both objects. The coronal jets are collimated ejections of plasma, and the theoretical modeling focus on the jets in open field structures, like this from Wiper et al. 2018, where they have the open field lines here, the straight field line here, with a bipolar structure, is a parasitic bipolar structure that produce this quadrupolar configuration with a null point. They introduce energy by sharing the foot points of the bipole that produce the ejection of the plasma along the open field lines. We are going to follow this kind of modeling that is called the embedded dipole. We have an ambient field, embedded null point, embedded dipole producing a null point, and we energize the system by sharing the foot points of the system. The solar prominences are cool plasma levitating in the hot ambient corona, and they are supported against gravity by the magnetic field. The magnetic field is much larger than the prominence itself, the cool plasma, and it is called the filament channel. The filament channel is the skeleton of the prominence, and it's larger than the prominence itself. In this picture from Chow et al. In 2018, this is just one example. We can see the filament channel here in the field lines, and the prominence supported against gravity in the deeper region of the prominence of the filament channel. Okay. Then the motivation of this work is combine both objects, the jets and the prominence. We wonder what happens if the jet is produced inside the filament channel and what happens with this interaction. Then the idea is just to put this bipolar structure inside this filament channel and see what happens. There is already observation about this. For example, in Luna et al. 2014 and Chang et al. 2017, they show that a jet in the filament channel that hits the prominence and produce important displacement of the cool plasma and oscillation of this plasma. This is the example from Luna et al. 2014, where we have here the SDO AIA in 171. The prominence or the filament is seen in absorption here, and we will see here the jet. Let me stop. You can see here very clearly the collimated plasma emanating from this point and perturbing all the filament. You can see the plasma moves back and forth, and the system oscillates with some period. And doing the time distance diagram, taking a slit here, we can see perfectly well the oscillations. This is the arrival of the jet, and after that, the cool plasma seen in absorption, a black band here, oscillate. Then this is the motivation of our work. Then our numerical configuration, we have the initial setup, we have the filament channel structure, is this. It says the large scale magnetic field. The prominence will be is loaded here at the center, where at the region of the deeper field lines. And we have also a parasitic bipole here, resulting in a null that results in a null point here that we will produce the reconnection here. We have also a stratified atmosphere with the chromosphere, transition region, and corona. And we will do simulations. We will perform simulation with the Mancha 3D code from the IIC. And we will shear the plasma below the arcade, the parasitic arcade that we have here. Okay, we energize the system, as I said, by producing the shear, by shearing the foot points of this dipolar structure. This is a detail of the previous picture. Then this is the velocity profile that is in perpendicular to the screen, as we can see here.
Sorry, your slides are not moving.
No?
No, it's stuck at the movie and the time distance slice.
Okay, let me stop again. Stop sharing. Can you see them?
Not yet.
Can you see now the slides, or?
We don't see it here. I don't know. In the
Yeah, we also don't see it.
We can't see also.
Now?
No.
Not yet.
I think Manuel need to relog into Zoom, just
Yeah.
like what happened yesterday with Durgesh.
Yes. Yeah.
Okay, let me stop then. Now, can you see the?
Yes, we can see. Yeah, please make it full screen.
Okay. Now?
Okay.
Okay. Let me say again this. Well, this is the filament channel structure, the large scale filament field, the prominence loaded in the deeper part, and also the parasitic bipolar structure. And you can see the change of the slide, or?
Yes, we see the changes.
Okay, then this is a detail of the previous picture, where we have the arcade, the parasitic arcade here, and this is the velocity profile where we are going to shear the field lines in order to inject energy in the system and produce the reconnection and the jet. We shear only in the first 20 minutes with 5 kilometers per second velocity, and this
Manuel,
is
you have 3 minutes.
Okay, this is what we have. The ejection of the plasma along the filament channel structure. This is a detail just around the reconnection site. Okay, this is the current with time. This is the magnetic field, the velocities, but we are interested in the currents around the reconnection site. And this is the breakout reconnection here in this current sheet. And the second phase is a eruptive reconnection. Well, we call eruptive jet produced in this second reconnection. After that, the system reaches again the equilibrium. Then we have two phases, the quiescent jet and the eruptive jet, associated to the two reconnections that we have. Then, what disturbances emanate from the jet source? This is what we wonder, and how interacts with the prominence. It's just in the bibliography, it's not very clear how the jet front travels, because they are focused just in the region of the source of the jet. And we have found that we have basically three perturbations. We have an Albany front that moves faster than the flows. The first jet is the quiescent jet that moves in the already perturbed magnetic field. And the second, and the third perturbation is the eruptive jet. Okay, this is a brief description of at the beginning, we have the basically vertical oscillation associated to the mass loading, but after that, we have, this is one typical field line. The color is just the longitudinal velocity, and we can see what is happening. The reconnection produce the perturbation transverse to the magnetic field, producing this oscillation in the horizontal direction. We can see here also the top view of the same picture. Okay, I'm not going to in detail. And this is the first jet, because this is the quiescent jet. It reaches the prominence first at the bottom, and it moves up in higher levels until the top of the prominence. Okay, the jet front is a shock that moves with 260 kilometers per second, and the behind flows is around 150 kilometers per second. Okay, this is the secondary phase of the jet. This is the quiescent jet that moves from the top to the bottom of the prominence. Okay, it reaches, we can see here, I'm sorry I didn't tell you, that this is the prominence. This is the mass of the prominence. We can see how the jet moves.
The screen is frozen again. We see the slide Albanic front.
Okay.
Yes, it is the same here.
Can you see now?
Yeah, we can see your screen. Yeah.
Okay. Well, basically, I'm going to just to summarize. This is the jet. This is the longitudinal velocity along the field. You can see how it reaches the bottom, and after that, it moves fast. It moves in the higher levels of the prominence. And the eruptive jet is the second phase. It moves from the top to the bottom. Basically, the jet reaches first the bottom, the top, and from the top to the bottom again. This is what is happening in the two phases of the jet. Well, this is a movie of the full event. You can see the mass here, the density. The jet reaches the prominence and moves to the other side. In fact, at the top, it moves the plasma to the other side of the structure, producing drainage of the plasma. And this is the different velocities, the longitudinal and the perpendicular in the y direction velocities. And we can see that this is the velocity in the cool part of the prominence. And we can see that it moves in the horizontal, but also in the perpendicular direction. And then we can see that this jet produced important perturbations of the system and perturb longitudinal and transverse motions in in the prominence. Well, as we conclude, I conclude that this is the first study of the interaction of the jet prominence. We have an organic disturbance moving ahead of the jets. Two stages in the jets, the quiescent and eruptive, and the jet produce important displacement and oscillations in the prominence, in simultaneously in the longitudinal and transverse motion. And this work has been recently accepted in APJ. Thank you.
Yeah, thanks, Manuel, for this wonderful talk. Okay, so now we'll see. I do not see any raised hand. Yeah, if anyone has any question, you can just straight away speak. Okay, I guess there is no questions. So, so thank you again.
Thank you.
Yeah, thank you, Manuel. We move to the next talk by Oscar Steiner, MHD simulations of small-scale magnetism and vertical flows. Oscar.
Okay, do you see my first slide?
Yes.
Okay, and you can hear him.
Yeah.
So, good afternoon, Bangalore. Still good morning here in Freiburg, at least for me, and west of Freiburg. I'm very happy to be part of this conference and part of the 50-year jubilee of IAA, which I actually had the chance to visit several times some 15 years ago when I had a collaboration with Siraj Hassan at that time. And we had at this time a common exchange student, which was Vigish Gangadaran. And Vigish is now since quite a while here at the Kiepenheuer Institute, and among others, working on gravity waves. Anyway, since that time, I was kept always being interested in what's going on at IAA, and I have from time to time also collaboration with Raj Guru. So I'm talking about MHD simulations of small-scale magnetism. This morning we heard from Reinier and Matthias, huge scales. These are really tiny small scales, negligible scales for them. And I concentrate on vertical flows. Well, let me here change something. Okay. And that is my outline. I start with a brief history of swirls, and we'll talk about the simulation of photospheric swirls, then move to the chromosphere and talking about the alphenic nature of chromospheric swirls. And in the last part, I will change topic a bit and look to a very different kind of vertical flows that occur at the edges of granules and which we now think may be connected somehow to the small-scale dynamo. So it all really started to take off with this seminal paper of Bonnet in 2008, where they observed, is there some additional noise, or do I need to switch off something? Okay. When they showed that there occur everywhere swirls in the photosphere, and they showed a particular nice example, which is shown here, and I try to show the corresponding movie. Maybe I make a loop, and then you see a nice string of magnetic bright points that get engulfed in the center of this swirl where these magnetic elements seem to coalesce and merge. This is a particular nice example of a photospheric swirl. There has been actually a precursor of this paper by a letter in Nature in 1988 by Peter Brandt of the Kiepenheuer Institute and collaborators, who observed with the Swedish Tower telescope and correlation tracking, and they discovered this nice swirl that is shown here. I hope you see my cursor, my hand up here. And at this time, we thought this is a kind of an exotic and very once-in-a-time event. But after Bonnet and co-workers, there has been a whole range of observers using different telescopes, different diagnostic tools, and they came to the conclusion it's not at all unique. They occur everywhere in the photosphere, and actually they gave some number densities. But already Peter Brandt noticed or conjectured that such vortices might provide an important mechanism for heating the stellar chromospheres and coronae by twisting the foot points of magnetic flux tubes. And that's why, of course, these swirls are of some interest. What about the chromosphere? So it was Sven Wedemeyer and Luc Ruppe van der Voort in 2009 who detected this nice swirl down here in the chromosphere in narrowband filtergrams of chromospheric diagnostics calcium infrared triplet line. You see this kind of hurricane or typhoon kind of object in the chromosphere, and right beneath it you have this magnetic bright point, which we know it's magnetic flux concentration. And so it is pretty obvious that there must be a connection between this photospheric magnetic flux concentration and these chromospheric swirls. But what is this connection exactly? And again, there has been a whole range of observers that used different telescopes, different diagnostics to observe these chromospheric swirls. And you see this table is not finished. It is out of a review, ISSI review on vortex motions that is in preparation right now. And then was this letter to Nature by Sven Wedemeyer and collaborators who showed that these chromospheric swirls have an extension. On the one hand, as I mentioned already, downwards, you see a bright magnetic bright point, and in the corresponding magnetogram, you see the magnetic flux concentration, but there is also an extension upwards. In that you see enhanced emission here in a transition region line and even in a coronal line. And that makes it, of course, interesting. Now let's move to simulations. This here on the top right panel is a horizontal cut of the density in a simulation box of Irina Kitiashvili, which is located a little bit beneath the optical continuum surface tau equals 1. So already in the convection zone, but really close to the surface. So you see still the granulation. And you see here the intergranular lanes, which have actually enhanced density because they are cool, downflowing, cool material. And within these intergranular lanes, sometimes also a little bit on the side, you see these holes. These are density holes. These are holes of reduced density. And these holes are surrounded by a swirling motion, as is shown here in this inlet. And likewise, Moll with the Muram code, he showed at the vertex of granular lanes, strong vertical flow. And in the center of this flow, there is a reduced gas pressure in this case. And we think this is coming from essentially angular momentum conservation. You have a downflow And you have, we call that sometimes, well, Åke Nordlund already called it originally the bathtub effect. So if you plug, if you draw the plug in the bathtub, you get this swirling water and it has a funnel shape. And this funnel shape reminds of magnetic flux tube, which make bright points. But here we have a funnel shape that is produced by this swirling motion, and they also produce a bright point. Feeble, more feeble than in the magnetic case, but there is also a bright point. And this is from a Murham simulation on the, from a Cobalt simulation. On the left-hand side, you have a simulation with magnetic field, and you see all these bright stuff, which once upon a time was called the filigree. And sometimes you have just a bright dot, which is really looks like a magnetic flux tube. On the right-hand side, we have a non-magnetic simulation without any magnetic field. And still, you also have bright points here. And they come from these swirling motions. And I can, oops, can I? Yes, you should now see the simulation. And I stop at some point when there is a particularly nice point. I think here now, there is a non-magnetic bright point occurring, and I go a little bit slower, and you see it's moving along the intergranular lane, much like a magnetic bright point. And if you watch this simulation long enough, you see all over the place these non-magnetic bright points occurring, which is a effect of swirling motions. What about the chromosphere? If we make a horizontal cross-section in the chromosphere, in this case 1,300 kilometers above the optical depth 1 level, then we see these flow cells. These arrows are plasma flow, and where these are diverging flows, and where they meet these different cells, you get a shock wave. And in the background, you see in grayscale the temperature. So you have these temperature peaks, and it's a complicated network. And if I don't have a movie now here, but they move very quickly. But you don't see any swirling motion here. But if you start this same simulation with say a homogeneous vertical magnetic field at the beginning, then it looks like that. And you have all over the place swirls. So clearly, while in the photosphere, the previous swirls we were looking at, they spontaneously occur as a consequence of angular momentum conservation and downflows. In the chromosphere, it's quite different. They only occur in connection with magnetic fields. But what is the connection? Is there any connection between these photospheric and swirls in the surface layers of the convection zone and these chromospheric swirls? There has been essentially two views on this. Sven Wedemeyer and myself had the idea, well, imagine you have a swirl in the surface layer of the convection zone, and there is magnetic field advected or attracted or engulfed by this swirl. As we have seen in the movie from Bonnet and collaborators, you have seen whole magnetic flux concentrations being attracted into this swirl. Then you can imagine that such a magnetic flux tube starts to rotate. And so in the upper layers in the chromosphere, where beta plasma is maybe smaller than 1, it drags all the material with it and produces these chromospheric swirls. Sergei Sheliak, on the other hand, he said he looked at Murham simulation and put test particles in there and looked at their movement and came to the conclusion that they move in a wave-like fashion with a rapidly changing and oscillating velocity field. And they identified this velocity field as torsional Alfvén perturbations. And they did not see an immediate connection with these magnetic flux concentrations in the photosphere. So we had a closer look to this and came to the conclusion that the truth maybe is somewhere in between. This is here a small field of view of a larger simulation, and this is a time sequence. And you see here a magnetic bright point in between, in the interparallel lane here. And up here is the corresponding magnetogram. You see already, when you have a closer look to this pattern here, that it is clockwise rotating. And correspondingly, down here, this is a proxy of a chromospheric diagnostics. We have here this kind of hurricane-like swirl in the chromosphere. This looks very much like what was observed by Wedemeyer and Rupe van der Voort. Now, what we did, we put an axis, a line of sight, a vertical line of sight into the center of this swirl. And we plotted along this vertical line of sight a quantity which we call lambda. This is the swirling strength. You can think of it as the vorticity. It's a generalization of the vorticity. So we plot that along the axis and with time. So we get a time distance plot. And now you see that the swirling strength propagates upwards. And when we plot a hypothetical test particle that moves with bulk speed plus Alfvén speed, it goes exactly along the path of this swirl. And this is a first indication that indeed we deal here with an Alfvén wave. Next, we look at the velocity streamlines at the bottom of the chromosphere. It's taken here at 700 kilometers height. And you see here rotation, clockwise rotation. And if we do the same thing with the magnetic field, we see counterclockwise rotation. And this is exactly what you expect of a torsional Alfvén wave, provided that the magnetic field points in the upwards direction. Opposite rotation of velocity and magnetic field in case of the magnetic field when it of the perturbation in magnetic field and velocity when the magnetic field points in the upward direction. And that's a second indication that we deal here with a torsional Alfvén wave. Next, you know, when taking the curl of the momentum equation, either in hydrodynamics or MHD, you get an equation for the vorticity, a dynamical equation for the vorticity. And that equation has different terms. Stretching term, famous baroclinic term. In MHD, you have an additional magnetic baroclinic term and a magnetic tension term. Now we prefer to work with the swirling strength, not with omega. Omega is the curl of the velocity, and swirling strength comes through an eigen analysis of the velocity gradient tensor. And we prefer to use the swirling strength lambda because it is 0 when there is pure shear flow, while pure shear flow produces a lot of vorticity. So we think lambda is a better quantity to look really at swirling motions alone. And we managed to derive a dynamical equation like for the vorticity for the swirling strength. It's recently published in this paper. And now the great thing is we can look at these different terms and see what is driving the swirl. And we found it's this term here which drives the swirl as it propagates upwards. And this term is, of course, magnetic tension. And that's a third indication that we have here an Alfvén wave, because those are driven by magnetic tension forces. But, and now comes a big but, we don't have an oscillation. We have all the time 4 minutes. That's basically the lifetime of this swirl. We have always the same rotation. And the color here, down here, indicates swirling strength. It's always the same color. So the conclusion is we don't have a oscillatory torsional Alfvén wave, but we have a unidirectional torsional Alfvén pulse. Somehow that pulse is triggered, and we still don't understand how that triggering really works deep down at the bottom of the photosphere. And it is just a kind of a jerk in one direction, and then this pulse propagates upwards into the chromosphere. And this is actually also the conclusion of Liu and collaborators from the Sheffield group, which did observations, came from observations and modeling to this conclusion. Here we have shown that these pulses emerge self-consistently in a fully self-consistent simulation. Often, if we have a more complex magnetic structure, like here, then we often see that in different parts of this structure, we have different rotation senses of swirls. And in this case, we have a superposition of swirls that may not show up nicely like a hurricane in the chromosphere. Yet, these superposition of swirls typically produce quite a bit of Poynting flux. And we obtain a mean Poynting flux over this field of view of about 12.8 kilowatt per square meter, which is quite a lot. However, this must be taken with a grain of salt, because it depends on the initial condition of the magnetic field first, and second, it drops very quickly to 0 towards the top boundary because of our boundary conditions, which forces the Poynting flux to become 0 at the top boundary. Now I would like, in the reminder, go to a very different kind of vortical flows, which occur at the edges of granules. This is an observation here with the sunrise telescope. And I would like to draw your attention to this central granule, which already has a kind of a sharper edge here. I hope you see my hand I put on. And then this rim here moves into the granule. You see a bright leading rim and a darker rim that is trailing the bright one. And we call that a granular lane. And this is quite common. You see actually also down here in this granule, and in simulations, you see that all over the place. But virtually every granule develops at some point such a granular lane. This here shows in the top row simulation, in the bottom row observations with the sunrise telescope. And you see typical here is a granular lane, down here similar. Excuse me?
You have 3 minutes now.
Oh, 3 minutes, okay. And here is another case. They look very similar. And now the great advantage of simulation, of course, is that you can make a cross-section through this granular lane and see what it is, and you come to the conclusion that it is a swirl. And since that goes along this granular edge, we call this a vortex tube. Now, recently, Matthias Rempel has looked at an exploding granule. You see here this big granule, in the center, it starts to get dark, and you see the development of a granular lane. And when you look at the magnetic field, you see first in the downflow a concentration of magnetic field, but after some time, few minutes only, you start to see magnetic field coming up. And clearly, this is transported by this vertical flow, by these vortex tubes that first drags magnetic field down and then back again up into the granule. And Matthias has shown that there is quite a bit of shearing of magnetic fields and intensification of magnetic field connected with this process. Now, recently, Catherine Fisher from the Kiepenheuer Institute has looked at a granular lane here and has done polarimetry. And as you see, this is a nice granular lane that moves into the granule. And after some time, you see the appearance of this green stuff, which is linear polarization. And this is more coherent. It's not so mixed like in this case, but more a coherent horizontal magnetic field. And we looked at our simulations to find events that look like that. And I best show now immediately the simulation. And you see down here, you see the continuum intensity. And look here, there is a granular lane evolving. As I go in time, you see it very nicely as it evolves. Now I go back. Then you see up here, at the beginning, we have a horizontal flux bundle in the intergranular lane. That happens sometimes. We have also vertical magnetic field. And here you see already in this cutout here, in this circular cutout, that there is this vortex flow. And that vortex flow drags magnetic field downwards, and it starts kind of to get twisted, stretched and twisted, comes up again. And as it comes up, it shows up as linear polarization down here in the intensity map. And finally, it would be, unfortunately, it doesn't go long enough, it would be transported back into the intergranular lane. So if one could, if we had highest polarimetric accuracy and high spatial resolution and high temporal resolution, we could essentially follow observationally this complicated topography of the magnetic field. And there is the hope that one could directly see kind of this stretch, twist, fold mechanism that is at the basis of the small scale dynamo. So there is hope to observe the small scale dynamo directly. Now, that's the conclusion. Simulations and observations alike show swirls commonly occur in the surface layers of the convection zone and the deep photosphere. Chromospheric swirls are produced by unidirectional torsional Alfvén pulses that propagate along magnetic flux concentrations in the chromosphere. The swirling strength is an effective tool for the analysis of vertical flows in the solar atmosphere, and we derive the corresponding dynamical equation of it. And finally, the vertical flow of granular lanes is capable of recirculating magnetic field from the intergranular lane into the granule and back into the intergranular lane on a shallow path. And it may be an important component of the small scale dynamo, which might allow us to have a glimpse on the action of this stretch, twist, fold mechanism of the small scale dynamo. Thank you very much.
Okay, thank you, Oscar, for this wonderful presentation. Okay, so now we'll take some questions. So first question we'll take from Rob Rutten. Please unmute and ask your question, Rob.
Yeah, okay, yeah, please. Oski, thanks for a fantastic talk. You were the best speaker that I know, and you did it again. And you were even the only one on this whole meeting that is speaking in 3D rather than 2D, because you're moving your head all the time like you do in a real talk. But so now I said a nice thing and now I can get nasty.
Yes.
I think you're missing out on the heating of the quiet chromosphere. When you look at the heating of the quiet chromosphere that you see in AIA 304 and also in AIA 131, then you see that these are big patches that are made by things that go horizontal. And in your simulation, everything is going up, and in Sheljag's simulation also. So I want to see these things that go horizontal, and those are the RBEs and the REs that Luc and colleagues have discovered at the SST. And so they go sideways, and we don't have a mechanism that makes them, but we know they come from network, unipolar network, bipolar network, doesn't matter. And so very, very likely the exciting mechanism for these, which is not reconnection, because then they would be element bombs, and they are not element bombs. So the exciting mechanism must be something like this. But so this means that in your simulation, you need to look at things that go much further and that go sideways. And the only simulation I've seen that I think is yet unpublished that has a few of these is a Muram from Sanja Danilovic that she showed in the presentation some time ago. And I think she has a much bigger box, but she also has these swirls as exciters. And so I think that the game is to find the excitation of the REs and the IBEs. And my suspicion is that these swirls that have magnetic flux tubes in them are the reason, but you have to show that.
So when you talk of sideways, you mean the magnetic field that is moving sideways, or?
Yeah, obviously. In this IBEs, hydrogen gets ionized fully. And so it is so the gas is not neutral anymore. And so it must be magnetically guided to go where it goes.
So I mentioned that the process that excites these torsional Alfvén waves is not fully clear to us, and one that we need to have a closer analysis for that, the simulation. But one thing that came to my mind was indeed that maybe the photospheric element bombs could also excite, could be a process that could excite such torsional waves. And I was happy to hear this morning from Elena Komenko that if you have included the whole effect, then how you would have, it seems, a way to better dissipate these.
Yeah, but so the element bombs, you only the classical ones you only find in active regions. Now nowadays we have the small ones, the
small ones I'm talking about.
So they might be doing this, but so that is strong field reconnection. But they are more common than you would think. That is what Luc is finding in H beta, especially now, because it's sharper. But the IBEs and the REs are always everywhere, even in the most quiet network. And they make the chromosphere that I see in AIA. And so those are the fish that you have to catch. But I think you need a bigger box. But I think that those swirls may be doing it, but you have to look at sideways motion in a box that has field that is expanding around network.
Okay.
Yeah, I think now we can move to question. Yeah, so Krishna, can you please unmute and ask your question?
Thanks for this very interesting talk. I have a couple of questions. So in your simulations where these swirls rotate, the chromospheric swirls rotate, and then you mentioned the lifetime of about 4 minutes or so. So when they stop, the vortex flows in the photosphere stops, or how do they end at the end of the lifetime? If so, then I mean, if the vortex flows stop, then the natural reaction of the magnetic field, shouldn't it rotate opposite way at the end?
Well, then I didn't talk about the lifetime, and we didn't look at the lifetime in our simulations. There are papers in this list that I have shown you that also show lifetimes, and they are very different. For example, Kostas Tsotsu has observed a chromospheric swill that lived for half an hour. Maybe they have a different excitation, or they are really anchored in a photospheric swill that lives that long. But typically, they have maybe lifetimes of 10 minutes or even less. And what we looked at here are rather, we had a limited simulation time because we had a cadence of 1 second. So that gives lots of data. We had a simulation time span of only 10 minutes, something like that. So we looked only at the few swirls, and these are rather weak swirls. And so they come not necessarily from a photospheric swirl. They come from concentrations of magnetic field. And sometimes it seems to us it is sufficient that, say, a magnetic flux concentration is only a little bit distorted, and that triggers that torsional wave that then propagates upwards. And that gives then typically a lifetime of a few minutes by which this wave propagates through the formation height of chromospheric diagnostics.
Mm-hmm. Thank you very much. So I also have just another question that you explained that for torsional alpha wave, the velocity and the magnetic field sense of rotation should be opposite. Can you explain why?
Well, that you can study in this nice book, if you see it, I don't know, by Eric Priest. It depends on the polarity of the magnetic field. So if the magnetic field we defined in our simulation, the magnetic field points upwards, then the rotation is opposite. If it points downwards, then the rotation is in the same direction. It's kind of tricky, but in principle, it's simple to understand.
Okay, thank you very much.
So let's end this discussion. So next question is from Auditorium. I see this question.
Hi. So this is Rajaguru at IA Auditorium.
Oh, hello.
Hi. So Oscar, it was a fantastic talk, and also very nice to see you swirling around in your office. So, so I have two quick questions. So you have this dynamical equation for your swirling strength.
Yes.
When you compare the terms directly from the MHD equation and the swirling strength, if you plot the strength of the different sources, do you see a change in the behavior as a function of height for swirling strength and the actual MHD terms?
Well, I didn't fully get the question. However, I mean, when I said it's the magnetic tension term that dominates, it's only for the propagation of the swirl. But deeper down where the swirl starts, there are other terms coming into play. So it's not constant with height.
Okay, so in other words, if you plot this swirling strengths for the different sources, there's different terms in your MHD equation as a function of height, and you also plot the magnitude of the MHD terms itself, the source terms itself, not the swirling strength. If you plot them together, is there a change in the height dependence?
I don't understand what you mean with the terms of the MHD equation. I mean, we have the different terms from the swirling strength equation.
No, the same terms which correspond to stretch and twist and the baroclinicity and the magnetic baroclinicity and the tension terms. So all of them will have a corresponding swirling strength, right? Because you have derived a dynamical equation for your swirling strength. Okay, I think we can discuss that
Yes.
Yeah,
It's
so
getting complicated.
Take question from Anabda, please ask your question.
Okay, yeah, Oscar, I think great talk and beautiful simulations. And I noticed that both magnetic and non-magnetic, in both the cases, you got swirling motion at the photospheric level with a bright point at the center, which looked almost the same in both the cases, magnetic or non-magnetic. So I was wondering whether the physics is the same or very different. So presumably you are including radiative transfer in your code and many all other processes. Is there any qualitative way of understanding why the bright point arises and why it looks so similar both for magnetic and non-magnetic cases?
No, the bright points here, like this one here, in the magnetic simulation, are very different from these bright points in the non-magnetic simulation. These bright points here are produced by swirling motion. These are produced by the magnetic field. And now the magnetic field, you know, when you have a magnetic flux concentration, you have a depression of the tau equals 1 surface, yes? And that makes this famous hot wall effect that High-Hank-Sprout was already talking about. And that makes the bright point. There is no swirling motion connected with these where you have magnetic fields. Here we have bright points that are produced by swirling motion, and here it is the centrifugal force that produces this depression in the tau equals 1 line. So on the one hand side, we have magnetic pressure, and here we have the centrifugal force. It's not clear if we have not looked at this. I mean, we also have swirls here in the magnetic simulation, and these swirls also produce probably non-magnetic bright points. But maybe this one is a non-magnetic bright point, but we haven't looked so far at this. I should also say that these non-magnetic bright points have not yet been observed. It's not so, they are more smaller and less contrast rich than the magnetic bright points. So there is a big difference, and it's not so easy to observe. You would have to prove the absence of magnetic field basically by the observation. So it's not so obvious how to do that.
Yeah.
So yes, it's a very different physical physics behind it, yes.
But observationally, I suppose that just from white light images, it will not be clear whether they're non-magnetic bright, but one needs simultaneous magnetogram measurements also to establish whether it is so or not.
Exactly, yes.
Thank you.
Okay,
thank you.
So take one small question from Ronnie Kippens. Ronnie, please unmute and ask your question.
Hello, Oski. I wanted to, how are you? I wanted to ask you one more thing about this swirling strength. I mean, if we do quantifications of natural oscillations in stratified atmospheres, and we have the eigenfunctions, we are used to looking at the components of the vorticity. But how the hell would we look at it in terms of these swirling strengths? I mean, can you compute it from the eigenfunctions? Is it something that we should look at?
Yes, yes. There is also a swirling strength factor. And this is the eigenfactor of the velocity gradient tensor. So, and then the swirling strength is just, how is it again? It's basically the absolute value of the swirling factor.
But are you saying that we need to take eigenvalues based on the eigenfunctions that we can compute in stratified atmospheres? That's what you're saying. Somehow eigenfunctions of eigenvalues of eigenvalues or something. I don't know what.
I don't see what this has to do with stratified atmosphere. I mean, this thing, this swirling strength thing has been developed by people doing turbulence theory. And so they
but so that's why I guess there is a big difference in approach. I mean, I'm used to linearizing equations and then solving for eigenfunctions and eigenfrequencies. And I want to compute from these eigenfunctions that give me the velocity components from the perturbations. I want to compute the swirling strength. Is that possible?
We compute it just from the full velocity, you know. We don't.
Okay, thanks.
Yeah. Okay.
Yeah, we see that we get a lot of questions. So thanks for giving such an exciting presentation. So probably, yeah, I'll give this to Anusa. Anusa, you want to say something?
Yeah, we have had all the talks in this session. Once again, thanks all the speakers. And over to Rajguru.
Yeah, I also thank all the speakers for this session.
All right. Thank you, the session chairs, and thank you also to the speakers. So we now have almost 2-hour break. I think we have the public lecture. It's called the Weinbach Memorial Lecture. This is also an IAA event. It will be by, as you all have seen the program, it's by K.R. Srinivasan. He's the university professor at New York University. So he will be giving our Weinbach Memorial Lecture today. So we will join back at around 6:15 p.m. So the lecture is at 6:30. Okay, so I think I encourage you again to go to the Slack channel. I think that we had a lot of discussion now. I think there are more questions to ask her. So people who want to ask him further, please join the Slack channel and post your questions there. And all the speakers of today's session may give their answer in Slack channel. And also watch the posters and interact with the poster presenters. Okay, so have a good afternoon or whatever, good morning. And okay, I'll see you in about 2 hours. Thank you. We will close the Zoom meeting now.